All right, hello everyone. We are continuing our design review investigation about multicomputation. And we've been talking about, let's take a look here. We're looking at trace graph and causal graph. Okay, so trace graph. So this is an attempt to represent a computational process evaluating, in this case, the fourth Fibonacci number. Is that right?
Yep.
Okay, so let's see what actually happens here. So you say, it's always very dangerous to define an F here. This is the result from trace. Why is trace graph still blue here?
I didn't provide any code yet because there's still some pretty serious bugs in it.
Okay, but let's take a look at what this picture is actually showing. So F of 4 is structurally F4. Well, I don't really understand that, but yeah, okay. And then this red means an evaluation event. Is that right?
Yep. So the F and the 4 both evaluated to themselves.
Okay. And then the F of 4, I mean, why aren't you doing this in terms of events? Because this really makes it kind of hard to see what's going on. I mean, this is really, this dotted line is an event. Is that true? Is that right? That's an evaluation event.
What do you mean by event?
Well, what we've always been talking about.
I spelled out, so we have 2 kinds of nodes and 4 kinds of edges, and I spelled out what they are above.
Okay, fine. Okay, the nodes. Non-highlighted nodes are expressions whose parts need to be evaluated. Highlighted nodes, whose parts do not need to be evaluated because they already were evaluated.
Either because they were already evaluated or because the head has non-standard evaluation.
Well, but what about the 4 here? That doesn't need to be evaluated. Why isn't that
right? So in the output of trace, this is just represented as a singleton list. And so I split it up into 2 different nodes so that you have the non-highlighted node is from the just expression decomposition, and the highlighted nodes come from things that have evaluated.
Okay, non-highlighted solid edges go from an expression to an unevaluated expression for a subsidiary expression. Okay, so that's these kinds of edges here.
Mm-hmm.
That's a drill down.
So in order to evaluate F of 4, you need to evaluate F and you need to evaluate 4.
Right, but you are still retaining the memory that having done that, these reassemble in this way.
Mm-hmm.
That reassembly information, which we also had in these weird kinds of events in combinators, that reassembly event, I mean, maybe Nick has a comment on this. I don't understand reassembly events, okay? Because they're different from other things we've looked at. Okay.
Right. So you only get the solid highlighted edges whenever you had started with the solid non-highlighted edges. So only if you have subsidiary evaluations do you then have to
reassemble.
Yeah.
Right. Does anybody have a comment? Nick or anybody else have a comment about the reassembly process?
I think it's important because it's then when you can apply down values or up values, etc.
I know, but that's something we haven't seen. We saw it in combinators. We haven't seen it elsewhere.
I have it in the token event graph, this notion of recombination. I have 2 notion special functions, decomposition and recombination. That's how you make tokens out of states. So you have an initial state, then you have to decompose it into tokens. Then you apply your events, your usual type of events that act on tokens. Then the resulting tokens are getting recombined into into our next state or several states again.
And do transformations get applied to states or only to tokens?
Rules are applied to tokens or to a set of tokens. To any set of tokens.
But Jose just made the comment that you are reassembling to a state in order to be able to apply down values.
Right. So down values, up values, sub values, and up values are all non-highlighted dashed edges. So out of the 4 kinds of edges, the non-highlighted dashed ones are the only ones that are transformation rules.
Right. Which in our other world will be indicated with a yellow event edge. You know, it would have a dot representing the event. So the only actual event that takes place is this one here. Is that correct? Everything else is a decomposition or recomposition. Is that true?
Mm-hmm.
Okay.
The solid edges are decomposition and recombination. The non-highlighted dashed edges are transformation rules. The highlighted dashed edges are
what?
Are just kind of weird.
No, that's not an answer. What are they?
They go from an atomic expression that hasn't evaluated to that same atomic expression after it's been evaluated.
Why aren't they the same as the other dotted line?
Evaluates to itself, because if there were own values, then you wouldn't get that kind of an edge. So it's something that only happens when you have a value.
Right. If there were own values, it would end up with something that does this kind of thing, where you go from f of 3 to this f of 3, you know, this thing here.
Yeah, exactly. You'd have a non-highlighted dashed edge directly from the symbol to its value.
Right. So this is the case where the symbol evaluates to itself.
Mm-hmm.
Okay. All right. So here.
And Christopher suggested last meeting maybe having an option to just combine those nodes into one node and get rid of those edges.
These edges here.
Yeah.
Okay. But the key point is the red things are all recombination events, recombination processes.
Mm-hmm.
So essentially what's happening is you take it apart. Okay. So the issue is when things were taken apart, as they have been here, for example, you take it apart to f of 3 minus 1, blah, blah, blah. That is then the reassembly. Okay, so essentially what's happening is, in terms of these graphs, if the whole expression, if nothing evaluated in the whole expression, you would see the tree of the expression followed by the reverse tree of the expression, reconstructing the original expression again. Is that correct? You would see a tree and an inverse tree glued together.
Mm-hmm.
And so what's happening in reality is that the inverse tree never has transformations happening in it. It is merely a reassembly. Is that a true statement?
Well, you can have transformations in between the point when you deconstruct and reassemble.
Absolutely. Absolutely. But once you're in the reassembly process, I mean,
the reassembly is always just a one-step thing. Like basically, it's not even an inverse tree. It's always just these two levels. It's just the parts and then one level down to the new expression. You won't get arbitrary red trees.
But you are getting arbitrary green trees here.
Right.
But I don't quite understand that statement because
the red ones are strictly just the last step. Once all of the parts have evaluated.
No, but you've got to reassemble. Look, if we ran the same computation, but without, well, I guess on some expression, some deeply nested expression that doesn't evaluate, we will see a bunch of breaking down tree pieces and then reassembly tree pieces, and they'll be somehow symmetrical, won't they?
Yes, but each reassembly piece is always going to be one level like this.
Well, in the same sense that each disassembly piece is also only one level at a time. Right? If you've got 4 levels down, you disassemble 4 levels and then you
well, in the sense that, you know, you can disassemble and then immediately disassemble again. You can't, assembly is just once and done. There won't be any further assembly.
I don't understand that. Every level is once and done, but the same is true of disassembly. Go ahead.
I think Ian is just saying that here you have, for example, 4 consecutive green levels and then 2 red levels. So he's saying that you can have any number of green levels consecutive, but it's always 2 red levels.
But it isn't. It isn't. It isn't because you have to reassemble the whole expression here. If I had a deeply nested expression, I would go down levels.
You reassemble the parts of an expression.
Yes.
That's the only thing that it's not a nested operation. It's strictly a level 1 thing. You have an expression, you evaluate its parts, you assemble its parts.
Okay, but don't you assemble, having assembled its parts, you then go and assemble the things that came back from those parts, just like you're doing here? Or am I confused? In other words, a deeply nested expression.
Once you've evaluated the parts, you're just going to have a sequence of parts, and then you'll assemble them into an expression. You won't be assembling parts, get an expression, assemble some more parts, get another expression, assemble some. No. You evaluate all the parts of the expression, and then you make a new expression out of the.
Okay, but on the way down, you're doing that. It's f of g of h and so on. You've got an F level, a G level, an H level, right?
For the deconstruction steps.
For the deconstruction step, yes. But are you saying that the reconstruction step is only one step? It doesn't.
Yes, the deconstruction step is recursive. The reconstruction step is just a single step that takes place after all of this.
To pick on somebody, Christopher, do you understand this?
Not really.
The reconstruction step happens after all recursion has finished. So it is itself not a recursive thing.
But why doesn't it have to come up one level at a time? Reconstructing one level.
Because that's the reconstruction step from the previous level.
But that happens after the reconstruction step from level 2. After the reconstruction step from level 2 is finished, then you get the reconstruction step from level 1, don't you?
Right,
after you've put,
which is what we're seeing here. You know, the ones that are higher up on the page are reconstruction steps from earlier.
Exactly. But my point is, if there was no evaluation,
reconstruction step is just one step.
Of course. Just like the actual deconstruction step here is only one step. For 3 minus 1, it's only one step. But for a depth 2 expression, it's 2 levels, 2 steps, right? And the reconstruction here again is 2 steps. There's this one and then there's this one, but we have something more going on because we have an evaluation here. I think we have to see your trace graph thing.
They're just independent things, I think.
I think there's a symmetry between them. Do you think there is a symmetry between them?
The symmetry is if you introduce a deconstruction step, then later you have to have a reconstruction step.
Exactly. So for every deconstruction level, there's a reconstruction level.
And my statement is you can follow a deconstruction step immediately with another deconstruction step.
Yes.
Follow a reconstruction step with a transformation rule.
Okay, that's not obvious to me. That you're not following the reconstruction step with another reconstruction step.
Right. Look anywhere where you have
I know I can see because you've got evaluation going on here, right? I understand that. I'm saying if you had an expression that didn't have evaluation, I think you get a series of deconstruction steps followed by the reverse series of reconstruction steps. Am I wrong?
I mean, that sounds correct, but it will still be the case that all of the red highlighted parts will just be 2 levels.
Yes, I know. Each individual, look, they're going to be exactly like this. They're going to be the mirror image of this. Are you saying the green is just 2 levels? No, each individual green step is 2 levels. Right, but they
Yeah, I'm not making a statement about individual levels. I'm making a statement about what you can follow a level with.
okay, but you can follow a
You can just
reconstruction
keep
level.
going down green levels, but you don't do that with red.
What?
But you do not there's no continually reconstructing things. You reconstruct things and then you apply a transformation.
I don't understand. If there wasn't evaluation, this would go straight. Okay, if this didn't have evaluation, right, it would go straight back up. The 3 minus 1 would get an F wrapped around it, and then it would get the plus wrapped around it, wouldn't it? Just going straight from red levels to red levels. Surely that's correct. It recurses down, it checks things out. It is essentially tokenizing. It is breaking things apart into tokens. It's saying for any one of these tokens, is there a transformation rule? If yes, then we're jumping out in some other direction. If no, it's just going deconstruct, reconstruct, I think. Isn't it? I'm pretty sure that's right. I mean, we'll know for sure if you make a trace graph on something that doesn't evaluate.
Mm-hmm.
Anybody else want to comment on this? I think it just has to be this way. Go ahead.
Yes, I think you're right, and certainly we need many more examples and withhold attributes and things like that.
Right, but we need examples where it just doesn't evaluate at all, where all it is sniffing its way down into the burrows, so to speak, and then coming back up again.
Yep.
Now, and what we also don't have here is we have no for this, we can already see that there's space-like separated events. Okay, this event and this event are space-like separated, are they not? They could happen in any order, doesn't matter.
Assuming no side effects.
There are no side effects here. There are no side effects.
Space-like separation means, in this case, that they come from different branches of a deconstruction step.
That's correct. Right. And what we're going to see, remember, right. Okay. That space-like separation, we're also going to see, we're also going to see, kind of, what am I saying? We're also going to see, branch-like separation, when we have multiple possible transformations that can happen, which you do not have here. Am I making sense?
Mm-hmm.
Okay, let's go on. Okay, this is very helpful. We're getting there. Now, how close are you to having actual code that just does this in all cases?
I think pretty close. I just need time to work on it. What I have works for down values.
Okay, that's enough. That's really enough. We don't try and do every other possible kind of value and holds and everything.
The other values are crashing the front end. So
okay, well, whatever. It doesn't make any difference. I don't care. We've got tons to study just with what you have here. If it does down values, make sense? Does it do down code as well? Yes, it does, because we've got one here, right? That's absolutely enough. Please do not go on and work on other stuff with this until we've had a chance to really play with this. So could I run the code that you have now for pure? Yeah. Okay. Great. Wonderful. Okay. Visually, this isn't quite right, because we're going to need. Maybe Nick is about to show us something that has more event oriented, because this is the main event is that transformation right there.
Yep.
Yeah, right. It's just below. The version of this event is explicit.
Okay. 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 Wait a minute. So this is showing a causal graph of that event, I'm now totally confused by this now. What does this mean?
Well, this is just those events from this causal graph derived from that graph above, maybe the older version, where the events are exactly those dashed edges.
Okay.
Evaluation edges.
Okay, and this is showing the causal interdependence of those evaluation edges.
Right.
So it's a little bit confusingly upside down for me. Oh, maybe it isn't. I mean, that event has happened. In what sense does that event cause the 3 minus 1 goes to 2 event?
Well, because 3 minus 1 appears there, right?
Yeah.
You have to make this 3 minus 1.
I see. Right, that makes sense. But so, okay. So this is, if we were to make the full token event graph, maybe that's what you're about to do here, where we see both the tokens and the events. Wow, what's this? Okay. Let's just move this out. So you're saying okay, f of 3 by an event goes to this.
Right.
Now, in like a string rewriting system, we're not explicitly showing the burrowing into the string. Just as we're here, we're just saying, see, what's really confusing here. Oh, I see. This is a state-based thing. So is it the case in this picture that every single state is equal to f of 3?
Well, they're tokens.
Yeah.
The tokens.
Yeah, that's good.
The tokens are all for a single state, though, right, Nick?
Yeah.
Yeah.
So what you're saying is, in this picture, oh, how interesting. Okay. So this is sort of quantum mechanics or something. This is the state of the whole universe. And this is saying these are equivalent states of the universe related by events. And what we're seeing here, so in the end, f of 3, we're interested in it going, this is actually a very nice picture.
But this looks like it's all possible of evaluations. If you go up a little bit.
It is all possible evaluations.
Okay.
Whereas in Ian's graph, what's the relationship between these two?
So the one on the right is just replacement rules, right? Like I don't think that's accurately always going to show what the evaluator does. You need to write your replacement rules and get something that gives a similar output as trace. Whereas trace graph, I'm converting the output of trace into a graph.
Sure, multi-way version is a hack right now. You have to specify all the rules manually. You don't extract it from the down values automatically.
Mm-hmm.
Okay, but what you're saying is this is the multi-way version. Well, this is a token event graph, which is by the nature of token event graphs multi-way. Correct? And this is a single way evaluation, correct?
Yeah. In the relationship section, there's a single way version extracted from the multi-way.
Okay,
Like
so there's
this
the
one's-
multi-way version. That's the pure causal graph.
That's a multi-way causal graph. Yeah.
This one here.
Yeah. Well, those two.
Yeah, right.
And this is the single way that corresponds to the one path that evaluator takes. And it's the same causal graph as above. The
Is it
isomorphic.
just
Because of
the
causal
leftmost one?
variance.
Yeah.
Okay. You mean you're saying this is the same as Ian's graph, or what?
Well, the same causal graph as the one that extracted directly from the Ian's graph above. So this causal graph is the same as the one above.
Which one above? The one, sorry,
Another
one
small
here.
causal graph. Yeah,
as
this
this
is
one
the
here.
same causal graph. Yep.
Okay. The causal graph portion of this, in which that event is recorded as being that token goes to that token. Is that correct?
Right.
Oh, it doesn't look right. It doesn't look right, because this here, these events here are only showing, they're not showing the ambient stuff around. They're just showing 2 minus 2 goes to 0. They're not showing where that appears in a complete state.
Well, they're not showing it, but they correspond to the same thing.
So there could be multiple identical things here. Identical 3 minus 1 goes to whatever could occur multiple times, but in different contexts. Is that true?
I don't think so. Like, this is how this would still show the same kind of thing.
I'm a little confused by that. But so, okay, so what you're saying here is this is a single way graph that says the evaluator goes f of 3, goes to this, goes to this, goes to this. So this is a particular path.
You can also think of it like I'm doing reconstruction all the way back to the initial expression, while the trace graph that Ian shows is just only shows the sub-expression, individual sub-expression. If you would follow the reconstruction every time all the way back, then that would be.
I see what you're saying. But again, in your graphs, every node is the whole expression.
Yeah.
So, and just like what we've done for strings, it is merely from that state, there are these events that can happen, but we're not well representing the drill down into the string to show where those events happen, which is what Ian is doing in this.
So, yeah, so I think the relationship is this. What Nick's doing is, correct me if I'm simplifying it, but it's a generalization of replace repeated. Like it's a list of rules and you're applying those rules just verbatim to expressions and applying them in all possible ways. Yeah. And the single way version is like find replace path. Like I've got this collection of rules, go from here to here.
It's not replace repeated, it's replace list repeated somehow.
Yeah. So the thing with the evaluator is that it's not like replace repeated. It's got a deterministic way of traversing expressions and
sure.
and repeatedly applying things during the traversal. And
yeah, I understand.
And that is what tracegraph is trying to represent with all those extra edges, is the traversal that it's doing to find where to apply transformation rules.
I understand completely. I think that is directly analogous to what happens with strings. Okay, so for example, if we look at, just pick up a random example of this. Okay, if we look at this, actually what I really want is, what is it called? Events. What is it called? The thing that shows both the states and the events. What is that called? Evolution events graph. Is that right? Anybody
something
know?
like that.
Okay. This here is doing the same thing that what the next thing is doing. In other words, it is just saying these are the possible transformations from BBB. It's not giving us mechanistically how to drill in to get to those things. Do you get what I'm saying?
Mm-hmm. Yeah, the two simplest cases for that would just be traverse it from left to right or from right to left.
Whatever. I mean, there are many different ways to do it, and there are many different ways to decide how many of these events you can happen. I mean, sometimes these events will overlap. Here they overlap. You can't do all three of those events together.
Mm-hmm.
Sometimes you can. I mean,
and also the evaluator is not a multi-evaluator. There's always a definite rule that will be applied.
I know. So in the evaluator, probably this one here, where the transformation happens at the first place it can, is what will get applied. So, okay, but what you're doing is you are breaking apart this step here, right? To say, how does it scan that expression and determine that that is the first transformation it can make?
Mm-hmm. I think the scanning and the choice of rule are independent, or, you can make different choices for them. Like two different rules could apply at the same place, or one rule could apply at two different places.
Sure, absolutely. But the
So
multiple
you want to
rules
be
can
able
apply.
to show both of those processes.
That's what the multi-way graph is going to do. It's going to show that's the branch hill direction. I mean, what you've got here, I mean, I'm a little confused. Can somebody help unconfuse me? I mean, in this case here, we're not, and in the case that Nick's showing, he's not bothering to show the substructure of how does it get to decide that BB goes to A and the first element is the correct evaluator path. Whereas Ian is showing us some of the breakdown of how you test these things. And I mean, what you're doing is a token decomposition or a state decomposition function. Basically, you're saying break the state up according to this tree as treeing, and at any stage in the subtree, you can end up doing the transformation. If nothing is transformed, then it goes back into a reflected tree and gets reconstructed again. So essentially, you're breaking apart this event step here into something that you can understand by recursing through that tree. Does that make sense?
Yes.
Okay. So, and now you've sent some mail here.
Make sure you save anything before you try running this.
Yeah, I just want to make a logistical point that Roger, are you aware of the meeting about category 3 design later on this afternoon? Did anybody invite you to that?
Yes.
Okay, good. All right. This is this. All right. So what I want to do is I just want to say, okay, trace of f of g of x. Oh, for God's freaking sake. Why does that do nothing?
Do trace original goes to true.
Okay, now I want to see that in your graph. How do I do that? Do I just say trace graph of trace, or trace graph of the trace original?
Trace graph of the expression with no options.
Magnificent. It just crashed completely. What's happening there?
I write the code in terms of pattern matching on the output of trace, and I have missing patterns, so it gets stuck in an infinite recursion.
And what, blows up memory and then crashes?
It should recursion limit or something though. Like, I mean, I think
That's what I would have
there's a
expected. I don't know
deeper
why the
bug
front end is
here.
crashing.
But why are you talking about the front end? What's the front end got to do with it?
No, I have no idea why the front end is crashing, but I'm saying that my code is definitely going into an infinite loop.
Right, there's some deeper bug that may be worth tracking down anyway.
Well, it seems worthwhile to find out what that bug is.
Okay.
I mean, very worthwhile. It's a crash bug. Has somebody run it in the debugger?
Nope.
Well, you need to do that. I mean, can you do that? Do you know how to do that?
Yep.
Okay. What was this? This is in trace graph here. Oh, did I just delete it? Was I down here? Oh no, I was, where was I? I was here. No, I don't know where I was.
Yep. That's where you were.
Okay. So do you think it works on any? All right, let's try.
It has bad behavior when things don't evaluate using down values and down code.
Okay, so 1 + 1 does that. It reconstructs itself. It probes kind of the subterranean things and then decides that there really isn't anything interesting there. So if I were to do this, okay, let's take a look at that for a second. So it drills, it drills, it drills. And okay. Okay, so that's the evaluation step there. Okay, so I think it really is true that this is a substructure of Nick's graph. That Nick's version, can I see Nick's version of this? How do I get that? Of that same trace graph.
I have a trace causal graph function. In the causal graph section, I think there's a.
But don't I want this kind of thing instead? If I want to get that function there, if I want to get that thing there, what do I do for 1 + 1?
You have to make those rules
by hand.
Yeah.
Okay, so this needs to be sorted out so we don't have to do that by hand. But I mean, so because what do you think this graph will look like in your setup? It'll have 3 events, if I'm not mistaken.
Yeah, I think so.
And at every stage, it'll be a complete state here.
Yeah.
I mean, can we encode it in what you've got up here? Could we encode that same?
Yeah, I think it's, you don't have to have these Fs. You just maybe modify a little bit that plus rule.
Okay, wait a minute.
And remove everything else.
Okay, so what do you mean modify the plus rule? We want to say A blank plus B blank. What do I want to do? Colon equals A plus B? Really?
No, you don't. You have to inactivate it somehow. So it's almost the same rule. You just maybe add times to it, or just use pluses altogether without times. So it's just the same rule.
I'm sorry, I'm completely confused. The same rule as what?
That's from the left, the one rule that involves plus.
This one here.
Yeah.
Sorry, where does that go? Let's see.
You're
Oh,
mapping
after
over a
the
list
material.
of rules.
Okay, so we want this, and then we want the corresponding thing for times.
You can just like add alternatives, inactive plus or times.
No, it has to go to the same thing on the right-hand side. Might as well just do this.
Yeah.
Okay, how do I feed in? I say inactivated of this, is that right?
Yeah. Inactivate your expression. Maybe add more parentheses.
Yeah. Okay. That's nice. So that's a multi-way graph. So Ian's analog of that is, let's put these side by side. Okay. Where do we see 2 times 1 plus 1 in Ian's thing? I don't think we do. Am I right?
Correct, because it never happens.
Well, what do you mean by happens?
2 never gets multiplied by 1 plus 1. It gets multiplied by 2.
But I'm confused here.
The other 1 plus 1 gets rewritten into 2.
Yeah. I don't understand. Why wouldn't there be? Okay, you're saying in the evaluator, as the evaluator is, this is what happens. It maximally rewrites these things because they're non-overlapping. And so it gives us always 2 times 2. Is that correct?
Yes.
But it certainly doesn't have to be that way. I mean, if we were running this in parallel on multiple processors, then Nick's version would be the correct representation of the different possible paths where either this one can be evaluated first or this one can be evaluated first.
It's a difference between deconstructing and reconstructing or just doing it in place.
I know this has got complete
so much to do
states.
with parallelization.
Okay, well, fine. But how would we represent the parallelization? Because you've got the parallelization represented because those 2 tokens are independently updatable, right?
Mm-hmm.
So again, okay, is it the case that that I can puff out this event into something involving your deconstruction reconstruction? Is that true?
I think you could have like an evolution of this graph at each node in the top graph. And you would see things expanding out in place. So like on that left branch, you see the 2, but the 1 plus 1 hasn't changed. So that would be like a stage in this graph where you would have blown out the 1 + 1.
Right. So it's a foliation in which
But
you
left the other
foliate.
one. The other one would still just be a
Right.
leaf.
But it's a foliation where you're going like this, and then you go up, well, there, above this. It's foliation in which this one has been done and this one has not yet been done.
Mhm.
Okay. Okay, let's make a roadmap for what has to happen. So I think, well, Nick, can you say, okay, first question is, in Nick's picture here, this particular example is confluent. Is that a general fact about is it the case that without side effects, it's always confluent?
It should be. Yeah.
Okay. So this is telling us, from Roger's point of view about parallel computing and so on, this is telling us within this graph are all possible histories with different pieces of the parallelism done at different times. What Ian is going to be able to give us is a more microscopic map of how that parallelism happens or doesn't happen with respect to sub-expressions. Am I correct? Does that make sense? Ian, can you speak to that, please?
I mean, I think it's like parallelization in time and rules.
Yeah, well, that's called space-like versus branch-like separated. Look, the different rules here. Okay, branch-like separation. Let's see, where are the branch-like separated things? Those two events there are space-like separated, is that correct? Well, we actually don't know. They could be overlapping. Nick or anybody else, can you say what the condition is?
Condition for what? Okay.
For branch-like versus space-like separated events. There's a simple criterion that if two events merge at a previous state, they're space-like separated. If they merge at a previous event, they're branch-like separated. I think that's right.
Maybe the easier criteria is when the same rule, maybe the same rule acts on different positions. Or maybe
Yes.
it's a different rule, same in the same position.
Yes. But the same rule, rules acting at different positions are space-like separated if they're not overlapping.
Yeah.
Which is to say that in a parallel computation, they could be done in any order.
Right.
Right.
Could that be a combinatorial problem? Because if there are n objects, are we going to have like n factorial different lines here?
Yes, if you can do them in any order, yes, that's correct. And that's exactly why that's the whole theory of global, local, and glocal multi-way systems, because there is much redundancy. Because we are looking at complete states here, what you say is correct, Jose. Even though those individual tokens, there might be 10 individual tokens, but there are 10 factorial ways of dealing with the whole set of tokens that might be updated, if that makes sense.
Yes, I'm just thinking of from the representation point of view, it will be a lot more complicated than having 10 parallel lines, as in Ian's graph.
Well, I mean, look, there is a trade-off, guys. It's the same thing in space-time. there's a trade-off between the nodes of the multi-way graph are complete states of the universe, in which case it's an incredibly wasteful graph, because the complete state of the universe is repeated many, many, many times with just tiny changes. Okay, the alternative is to keep track of the changes, but not say how they're assembled into complete states. That's the local multi-way idea, or the token event graph idea, usually. Nick, do you see how to merge what you're doing with what Ian is doing?
Well, that's, what amount of merging is required depends.
Well, I would like to see a graph that where I can turn a knob from going between global and local multi-way systems. Well, what you have right now is essentially a global multi-way system.
Well, if you talk about token event graph in general, then it can be, there are some knobs there that can go from local to global through local in any way you can.
Yes, but we need to see that because what we're saying here is
we have a prototype. It's like when I actually have explicit recombination of expression and merging them into states.
okay. Okay,
Wait,
cool.
Nick, is this just the one with the states are those mint green vertices?
Yeah.
Well, we've
Just
looked at those during
do you want to-
previous meetings. Yeah.
No, we have more than that. It's like,
Oh, okay.
You want to show
Uh,
something
it's-
quickly?
you can open it's in the working material, physics working material. It's called expression tag. I have just one example there. It's a mess right now, but it's in progress.
I don't understand this picture at all.
Well, this is now it contains all of those types of vertices, right? We have tokens, states, and events.
Right.
You start with the state. It can be decomposed into all sub-expressions, right? That's what makes the state. Then events actually, I draw it like events act on a state, but they actually act on tokens. There's like more tokens that you can add to this graph, actually, but I'm not doing it here.
Right. So in Ian's way of doing this will be broken into tokens, and then events would act on the tokens.
Yeah, that's actually what it's doing. It's just I'm just not showing it like that.
Right. Okay.
Those events act on tokens.
Okay. Each one of these is probably a single token being evaluated.
Yeah, it depends on your rule, but it in principle can be more than one. And then you collect all the outputs from all your events, and you make more states, and it can be more than one.
Mm-hmm.
Like in this example, you can make 2 expressions instead.
Mm-hmm. And that's a different rule there.
Yeah.
All right. I think we're progressing here. I mean, anybody else want to make comments before we wrap up here?
This reminds me very much of the difference between CVS and Git. In CVS, you keep track of the changes in individual files, while in Git, you always worry about the state of your whole file system, and you keep changes of the whole file system. And you have also 2 different sets of graphs.
Well, that's interesting. So you're saying Git is more like the global multi-way system?
Exactly.
Okay. Roger, do you have any thoughts?
Well, depends on what we want this to end up with. I mean, one possibility is that there is a family of functions that let you visualize and understand evaluation. And maybe
that's part of what we want. Yes.
Click and expand out something or contract something.
Exactly. Yes, that is part of what we want as a debugger, where you can say, how did the evaluation happen?
Right. In which case, we probably need to invent more ways to compress things.
Yes.
Or focus in on areas.
Yep. That's a different thing. That's a thing where this graph, if you drilled it all the way down, and this graph has to be dynamically built because you're not going to want to build the whole graph for everything all the time.
I think another concept that's I mean, it's sort of related, but working at a certain level of abstraction. So you don't want to see event below a certain level type things.
Yeah. Right. But okay. So one definite thing is the debugging process. The other thing is understanding is, the real thing we're going for is the general way of doing multi-way computation, because it's one thing to do our particular evaluation sequence. It's another to look at the whole multi-way graph and look at other evaluation sequences. See what I'm saying?
So ultimately, Stephen, what should an evaluation graph be able to do, like in a few weeks when it's ready?
Well, I mean, one thing it should do is be able to, I need to go to a different meeting here, but one thing that it needs to do is be able to, oh, wait a minute, 20 minutes. I don't understand this. Hold on one second. I'm now confused. What happened here? Oh, okay. Something got moved. All right. Okay. Fair enough. We have a few more minutes here then. Okay. Then let's review what we're trying to do. Okay. Okay. Remember, evaluation is a single way process.
I understand.
Okay. So one side effect of this project is good graph visualization of the single way process that is evaluation.
Right.
Thing number one.
Mm-hmm.
Thing number two is understanding how we get multi-way evaluation, which our evaluator does not do.
Yeah,
right?
Yeah, right.
So multi-way evaluation, I mean, Nick's token event graphs are doing multi-way evaluation. We would like to get as general a multi-way evaluator as possible. That is, we want a multi-way evaluator such that we type in an expression in our language, which would normally undergo single-way evaluation. Okay, but we want a multi-way evaluator for that. And in the past, it's like, what's the point of this? Because if there aren't side effects, it's going to give the same answer, whichever of those multi-way paths you take. If you get it all the way to the end. If you get to the fixed point all the way to the end, it's, well, maybe it isn't. I don't know. I don't even know. No, that isn't even true. Sorry, I take that back. It isn't true that you'll always get the same answer. But we've always been interested in the particular answer that you get from the single way evaluator path.
No, I understand all that. I mean, I understand.
So the second thing we want, I'm just clarifying for everybody else. The second thing we want is to be able to type in an arbitrary Wolfram language expression and see its multi-way evaluation graph.
Right. So one question there is, as Nick mentioned before with Fibonacci, so he can represent it as a tag, and he could probably even represent it with this nice, global, local graph he has now, but he still had to enter the rules manually.
Well, that's hopeless. That's absolutely hopeless.
Yeah. Hold on.
Right.
Yeah,
that's not what we want.
Yeah. Not done. Right. Okay. So ultimately, for a general evaluation graph, it can't be the case that you enter it manually. You want to just be able to enter any arbitrary expression in the language.
Yes.
And automatically you get the evaluation graph.
Yes,
right?
you got the multi-way evaluation.
Okay, so Nick and I have discussed this. Nick, he has some concerns about next steps for doing that. So let's address those now, I think.
Nick?
Well, my concerns are that it can be a mess. I don't know. It's like, what happens with all those language constructs? How do you then make them into a rules? How do you make a general multi-rule out of any Wolfram language construction?
Okay, let's restrict ourselves. Okay, so currently down code is single way. All down code is single way. Am I making sense? It has a definite answer. You feed an input, it gives an answer. Right?
Right.
I think that the answer is that the things that are represented as rules, like Stephen is going down, so there are all these rules, right? Down the values.
Yeah.
But there are also code that isn't rules. There's like you can't progress any farther. It's basically stops there.
Well, no, I'm saying that a pattern matcher is easy to generalize to multi-way.
Yes. So the things that are rules.
Yeah, they're easy to generalize. Now, other things like, I don't know, some polynomial operation where, like, for example, the plus operation. There is an obvious multi-way generalization of plus that involves, for symbolic x, y, z, the multi-way version of that presumably has x, y, and z in all orders and all parenthesizations, presumably. I don't know. I haven't thought about it. This is, in a very different world, this would be like some kind of quantization of a classical phenomenon. It is multi-wayifying things. And as I say, some things are very easy to multi-wayify. For example, so our rules are easy. Our functions, which evaluate their arguments, are also quite easy. If we make the assumption, which may or may not be true, that we can evaluate the arguments in any order. Well, it probably is true. For functions that evaluate their arguments, that probably is true. You can just evaluate in any order. Am I making sense?
Generally.
So, right. So it would be enough to understand what's going on if all we did here was we started off by saying, let's multi-wayify things defined by pattern matching rules. Am I making sense? Because there's an obvious generalization, right? There are pattern matching rules that are underdetermined where there are multiple matches that could happen. Yes? Right, it'll be X triple blank, Y blank, Z triple blank. That has many possible matches. And then what I would like to see is some standard problems that people do with logic programming, for example, or with the NP type problems done this way. See what I'm saying? Yes, no, maybe?
Makes sense.
I think the problem is it's like the way you multi-wayify this kind of rules. It's not by the rules itself, but the position when you can apply it. So if you're given a down value, there are multiple places where you can apply it. I think in general, it's hard to see maybe there's some scoping issues, like this rule can be applied here, but not there, even though it applies there by pattern matching. Like if it's inside of module or something like that.
Yeah, I understand. I understand. The full multi-wayification of our whole language is quite complicated, right? We're not close to that. It's a big language. It's got lots of scoping constructs. It's got lots of generated variables, all kinds of things like this. We are not dealing with that yet. Okay, we may want to deal with generated variables fairly soon, or at least simple cases of that fairly soon, because that may be a big piece of the story. Okay, because clearly, two modules that are being run in different branches will generate different explicit names for their variables. Although they were canonicalized to the same name, they are nominally different names on different branches. Does that make sense? I mean, that's what we've seen a whole bunch of times, right? Nick, you've written all kinds of code that does this, yes?
Oh yeah, but what you do with if you have a module, you have to use a down value for module. It's like how you unwrap it. Is it kind of a rule that you want to?
I know. I keep on saying, okay, our system is not a multi-way system. It is a single-way system. That's what, we have a giant code base of many tens of millions of lines of code or whatever it is, that is a single way system, right? What we are doing here is we're doing the investigation of slowly trying to make pieces of it multi-way. And the first piece to make multi-way is the pattern matcher. And what we will do is steadily in different pieces of the system, we can see how to make them multi-way. But how we make module multi-way, I don't know offhand. Does that make sense?
I think so. That would correspond to having multiple dashed edges, the non-highlighted.
Yes, that's right. That's right. That's correct.
You'd have the potential for multiple different ones, like the down value or an up value or a sub value.
No, it's nothing to do with. No. It's not all those different. It doesn't matter about those different ones.
Well, okay.
Down
the definition there may be more than one definition that could apply to it.
Exactly. In the down values, there could be 17 definitions that all apply, and they lead to different results.
Yep.
That's the multi-wayification.
And the other multi-wayification is the solid non-highlighted edges, like Nick has on the left, where you have every single sub-expression. The evaluator only looks at the parts at level 1.
Sorry, say that again.
So like trace graph has 3 edges out of there for the times and the 1+1 and the 1+1. If you multi-wayified that would be, you'd have edges not just for those 3 sub-expressions, but for every sub-expression.
Yes, I think so. Look, the full multi-way graph is going to be very big. Okay, we've said this 1,000 times, right? It's going to be very big. And worse than that, it may not even have a fixed point. Okay? But then what we are trying to do is we're trying to ask for different types of evaluation where it is not following a single way path to a fixed point, which is what we've been doing for the last 35 years or more. Okay? We're asking for example, look at all the possible paths and ask the one that, for example, gives the smallest number in this place or something, right? Different types of observers of the multi-way computation. Do you get what I'm saying?
Mm-hmm.
Okay, and let's just review again why we want that. Why do we care? Right? Can somebody, okay, we care because many styles of computation use something other than the input single way evaluation output model. Okay, for example, logic programming uses, is there a path that gets from here to there? NP problems. Is there a way to get to this thing that satisfies this constraint? Hash P problems. How many things are there that satisfy this constraint? Etc. Does that make sense? Or probabilistic programming, what's the probability? What are the different outcomes with what probabilities? Maybe somebody else has another example. Anybody else have another example? Roger, Jose, Tony, Christopher, anybody?
I was thinking of path integral type things.
Yes.
But I think that's very obvious. Yeah.
Which is more like probabilistic programming. But yeah, it's probabilistic programming with a phase for every path.
Yes, but somehow they interact, right?
Yes, that's what happens in these multi-way graphs. That's the whole point, is that there's branching and there's merging. I mean, the path integral case requires that kind of model of quantum mechanics, in which the branchial position is the phase. So moving around in branchial space is what corresponds to a change in phase. Well, okay. I think we're probably, sounds like everybody has gone silent here, so we're probably anything else that anybody wants to add here?
Well,
I mean-
just to review. So, I mean, in terms of what we'll be working on for next week, Nick, this next step of generalizing pattern matching multi-computationally, do you have any other concerns about that? Or do you think that that seems feasible?
That's what Nick has basically implemented with multi-replace.
I just want to make sure, like, while we're still on the call, before we depart.
Or I don't know what else should I do. It's like multi-replace. Yeah, that's right. It's you can use any rule and it just searches for different positions. If I have a down value rules, sure, I can use those.
Right, but I mean, I think it's sufficient. I think we need a function that just takes a bag of rules, not as down values, just a bag of rules. And, you know, // dot will do the single way evaluation with that bag of rules. Am I making sense?
Yeah.
And then what we want is the thing that makes the multi-way evaluation with the bag of rules. And by the way, that bag of rules may not even terminate.
I don't think it's a bag. I think it's like an ordered bag.
It's not ordered when it's multi-way.
No.
When it's multi-way, all possibilities are
Right.
used.
Then it is a bag.
Right. But I agree with you. In the evaluator, it is not a bag. It is an ordered list.
Yeah.
But how far away are we from already having that?
We're not very far. We just need it all cleaned up. And then we need... Okay, the other thing that Nick has done is to look at rules with patterns on both the left and right-hand sides.
Sure.
And that's a new and different thing, which may be needed. It is needed to represent theorem proving. Equational theorem proving.
Yeah.
Okay. Okay. So that's another piece that is not the pure replace list story. Right. And so what we should be able to get from this is something which is maybe not efficient at first, but is a theorem proving result. That is, we've got the multi-way computation. That's the entailment cone in our other language. And we've also got the theorem proving I can find a path type result.
Right.
Okay. So let's see that all explicitly with bags of rules that are, you know, patterns on the left-hand side going to literals on the right-hand side, and patterns to patterns. Now, what we also discussed in a previous meeting was utilities for patterns to patterns rules. In fact, in general, utilities for handling patterns. Like, we don't even have canonicalization for patterns as a built-in thing. We need a family of functions for handling patterns. Does that make sense? Nick, does that make sense?
Yeah.
I mean, you've already got one of those functions, so we just need to package them up.
Okay.
Okay. So now, all right. So for next time, I think what we need to have is bag of rules, and it will be useful if Ian's, if there can be a merger between Ian's stuff and Nick's stuff. And essentially what's happening is that /dot replace all is drilling through, you know, that's the kind of the burrowing operation of the evaluator, which we don't need down values for. We just can do that with rules and /dot. Am I correct, Ian?
No, we need a different kind of replace repeated for it to mimic the evaluator, I think. Because I think replace repeated, like...
Yes, I agree. It does not have the exact same evaluation order.
Yeah.
Yes, that is correct. /dot does not have the same evaluation order as the evaluator. You are right.
But I agree with you that there is a sensible thing of give me a list of rules and then traverse the expression in a bottom-up depth first traversal, and don't progress back up the expression until you reached a fixed point at lower levels.
Is that what the evaluator does?
Yes.
Okay.
And then after it does that, it does the whole thing again.
Okay, but so what you've got then is a traversal order that corresponds to the evaluator. But in the multi-way graph, you have all traversal orders. And you can define in essentially a tree traversal order, with that same language for tree traversal orders, you can define one traversal order, which is the evaluator.
It's traversal order plus the fact that it's an infinite evaluator.
Okay, fine. Well, we need to understand all of this, right? We need to be able to parameterize that. So this is what our evaluator does. This is an alternative evaluation order. And again, I'm reminding you again, the whole point is to be able to get things like logic programming where it is not a particular evaluation order. It is all possible evaluation orders, all possible evaluation paths, picking out the path that satisfies a certain constraint.
Yep.
Right? And we need a clean way to do that. And what I think we're going to find is a family of functions that do these different operations that are standard for this different model of evaluation. Okay. Now, meanwhile, quite separately, Roger is interested in what can be parallelized, I think. Is that a fair characterization? And in principle, how we run these things actually in parallel on multiple threads.
Yes. But also, I mean, I'm a pragmatic guy. I want actually sort of usable tools. So even if we can have language constructs that says, make this, what's semicolon? What's that? A compound statement. Yeah, compound expression. Like, you could have something that's like parallel compound expression, says independent.
Yeah, that's what we're calling multi a few weeks ago.
Right. So even markups like that makes the task easier to sort of, require less analysis, for instance, if the analysis is not always going to be possible. And so
right.
we want to be able to, automation is great, but even markup, like OpenMP is kind of markup, and our coarse-grained parallelism is markup, like parallel table and stuff. But we need finer grained stuff.
Yes, and separately, there's a separate project of looking at the multi-threaded evaluator as a practical, actually launching threads.
Yes.
But the thing that I'm looking for with all of this stuff, there are two endpoints as far as I'm concerned. When you think about computations, there's a certain way we think about them. But one of the things we don't do is what Prolog used to do and what we do with constraint systems of various kinds. Just say, here are some constraints, find me something that satisfies these. It's kind of the generalization of equation solving. That's what I want us to be able to do. It's a style of programming that I think will be useful. And obviously, it has the issue that Prolog had of you never know how long it's going to take and things. And that's part of the reason why I think that these graph type things are super useful, because they give one a lot more information about what's really going on. As opposed to the problem that people had with these kinds of programming models before, which is just it becomes a black art of whether the thing will ever terminate or not, or will terminate in reasonable time, because you had no diagnostics. Really, pretty much no diagnostics. Now, similarly with theorem provers, you've again got this thing about, I don't really know whether it's ever going to find the path, and there are very few diagnostics. But I think, with this, what we will be able to find is theorem proving, plus, in addition to the path it finds, we'll be able to find these kind of the tentacles hanging out towards nearby paths, and that will probably be quite useful. So it's enabling the style of programming, basically, and trying to make a nice formalism for what will ultimately be things that can be done as space-like separated computations. That is, computations which can be done at the same time in different places, so to speak. Does that make sense?
Oh, yeah.
Okay, we should wrap here. But I'm excited about, the real progress is being made. Now, I don't completely know. I mean, I know Ian has other things to work on, and I think it's possible that Nick should take over the main heavy lifting here. If I don't really quite understand what, I mean, Ian has clarified a bunch of what's involved in this kind of, burrowing into expressions and so on, which is very useful. And I don't quite know whether that should be do we need two different code paths here or not?
I think there is a smaller project here which is helping with the output of trace, which was the original motivation for what Ian is doing, and that might be a nice project on itself. And in fact, trace is the trace of our sequential evaluator. I'm wondering what is trace for a parallel evaluator?
For a parallel single way evaluator, trace will look very similar. It'll just have some space-like separated pieces. This thing we're seeing on the screen here on the right is basically a parallel trace. Just happens to have been evaluated sequentially with some kind of depth first traversal. It's going to look the same, I think. The issue is when you draw it foliated, if this is a time foliation, this picture that we're seeing right here is parallel.
Mm-hmm.
The sequentialized version of this, as Ian was just saying, is the depth first traversal of this thing. Is that correct, Ian?
The standard evaluator is a depth first traversal of the expression is what I meant. I don't know what a depth first traversal of this graph would necessarily be.
Well, because what's going to happen is this piece here is going to evaluate before this piece here.
Mm-hmm.
Right? Maybe it isn't quite depth first, but there's an ordering. This graph is drawn in layers where that layer there is a parallel layer. It's got this and this at the same level. So if this is time going down here, this is a parallel computation.
I see.
See what I'm saying?
Yeah.
The sequentialized version of this would, it would probably extend this.
I think that right branch would just be shifted down.
Yes, I agree. Yeah. I agree. That's correct. Right. I think that's right. I think that is what you would see in and it's perhaps worth even having that kind of picture available. The actual order in which things are done, reading from top to bottom. And by the way, these things here would no longer be across the page. They would be that one, and that one is lower on the page, that one is lower on the page, and so on. So their vertical coordinate records the time at which they're done. But
an example of a very tricky phenomena, which I don't know if we are on path to capturing in parallel, is when they are not space-like separated and they actually depend on synchronizing in the right order.
Exactly. That's branch-like separation. That's exactly branch-like separation.
But those bugs, finding those bugs.
I know, but that's exactly branch-like separation. That's the point. Branch-like separation is when there are multiple branches you could go, and the question of whether, so for example, when there is confluence, it doesn't matter which branch you took.
Right.
When there isn't confluence, it does matter. And what can happen is there can be locally non-confluent things where if you say, what happened at this moment, you say, oh my gosh, this piece ran, that one didn't, I'm going to get a different answer. But it turns out it doesn't matter in the end. There's eventual consistency.
Are there two kinds of confluence? Like you could do the same thing two different ways, or you need to do things on two different branches just to get the next step?
There isn't the concept.
It's like a causal relationship on two different parents instead of saying a causal relationship on one parent, but you could have chosen a different parent.
No, I think that what happens is if you have a single time slice, okay, a single way projection squashes out the branchial direction and makes a causal graph that is purely space-time. if that's useful. So in other words, if you say, I've got a sequential computer, I've got a non-quantum computer, so to speak, what happens? You have to squash the branch hill direction. You only get one set of things can happen. Whereas with the branch hill direction included, you have multiple possible things that can happen, which an ordinary computer, a theoretical quantum computer, not the actual ones because they have different issues, but a theoretical one could be doing all those things on different branches. If that makes sense.
Mm-hmm.
Was that an answer to what you were asking or not?
I think I was asking a slightly different question, which is like,
I think you're asking the difference.
Your wording about branching was like, you could have gone this way or this way, but what about the case where you want to go both ways and you need information from both directions in order to get to the next step? That seems different than just...
That is not classical computation.
Wow.
That's not classical computation. That's the case where
that reminds me of like the graphs and find equational proof, though.
Yes, find equational proof is a branch hill story. It's not.
It's not somehow like the different branches are different branches it could have taken. It took all of those branches and it needed them all to combine them together to get a proof.
No. Well, okay. You're getting that is the critical pair lemma story.
Mm-hmm. Yeah.
Okay, the critical pair lemma story is an optimization. It is not necessary. This is hopefully explicated somewhere in that 250-page metamathematics post that I just put out. The section on relationship to automated theorem proving, I believe, untangles this issue. That is,
I'll check it out.
Yeah, I mean, but that's a good issue. Right, that's a good issue, and critical pair lemmas are precisely this, branch hill interdependence. But they are, I believe, Nick may have a crisper comment on this. I believe they are an optimization. You do not need them. Because what you're doing there is using.
So, like, let's say you want to constructively prove P and Q. You'll want to get a proof of P and a proof of Q. And you combine them to get a proof of P and
exactly right. That's what we call a cumulative evolution in the metamathematics piece. I mean, but you don't need that. You could do. Well, I don't know. Nick, do you have a last comment on this?
I'm not sure. It's not what we're doing when we're searching for those proofs. We are proving qualities, so it's not P and Q. Right?
Yeah.
So if it's P and Q equals to something, maybe P equals Q.
I really need to go. So all right. Good stuff. All right, to be continued. Okay, see you guys soon. And by the way, there's at the top of the hour is our discussion about category theory, which for people on the live stream will also be live streamed. Okay, see you all soon.